Next, let us define the wave energy, which is basically the sum of the kinetic energy due to the wave motion and also the potential energy due to the displacement upwards or downwards from the still water condition. Now the wave energy is calculated per wavelength per unit width because the wave is very long in its lateral direction. So typically we calculate how much energy there is per unit width, per 1 meter width of the wave. Now the kinetic energy and the potential energy in the wave is interchanged because we assume that there's no energy dissipation. So um, that's why we see that the expression are exactly identical, whereby the kinetic energy or the potential energy are given as rho g h squared L over 16. So it depends on the wavelength and also depends on the wave height. If we calculate the specific energy or energy density, then we uh, divide the energy by the wavelength so that we get rho g h squared over 8, which is the specific energy or total energy per unit wavelength. The wave power or energy flux, which means how fast that the energy is being transmitted in the direction of the travel per wavelength per unit width per unit time, is given by P equals to N times E over T. And it is a constant if no energy is lost or gained from the wave. Now, since we know that a wave train have a constant wave period T, so that would also means that if wave power is a constant, then N times E is always a constant. Now, what does this tell us? Remember that in the shoreward direction, when the wave propagates, the N will slowly changes from 0.5 and eventually becomes equals to 1. Now if N times E is always a constant, it would mean that when N increases, the energy E must decreases. So as the wave propagates shoreward, the wave energy will reduces in the shoreward direction. We will look at how we apply this concept of wave energy and wave power in more detail in our subsequent lecture on wave transformation. We're going to begin by looking at the effect of shoaling. In order to do that, we are considering a wave that moves in water, whereby the water depth reduces gradually towards the shoreline, and we will neglect any other effect such as refraction or reflection. So recall that the wave power P equals to a constant, and since the wave period T is also a constant, so N times E should always be a constant. We have learned previously from the topic on wave mechanics that the wave energy E can be given by this expression. So if NE is a constant, we can write NE at one location is always the same as NE at another location when the wave moves. So N times E is given by this expression at location 1 should always be the same as N times E in location 2. And since rho g and 8 is the same on both sides of the equation, it cancels out. That's why we are left with only this expression, which tells us that N1H1 squared times L1 is always equals to N2H2 squared times L2. 1 refers to one location, 2 refers to another location. So when the wave moves from one location to another location, where the water depth changes, N value will change, the wave height H will change, and the wavelength L will also change, and they are correlated in this equation. If we rearrange this equation, we can write it in a form that looks like this. But you notice that here the slight changes in the subscript. Okay, we are going to write N1 as N0, H0, L0, or N0, H0, L0. We follow the notation that we used previously, whereby the subscript 0 refers to deep water. So let's assume that position 1 is deep water. So we have N0 times H0 squared times L0 equals to, here we drop all the subscript, it can be any location, so it equals to N times H squared times L. So if we rearrange, this is what we get right now. Okay, the H0, N0 and L0 is from this side. The H, N and L is from the right hand side. So now let's look at this equation. You can easily show how this equation comes from here. Okay, so you notice that in this equation we have H and H0. That means on the left hand side basically is the ratio of the water, the wave height H at any location compared to the wave height in the deep water. Okay, now if we write the entire right hand side, okay, which looks like this actually. Why? The right hand side N0 is the ratio of the group wave celerity compared to the individual wave celerity, and in deep water N0 equals 1/2. So the right hand side actually can be written in this form, whereby N0 is changed to 1/2. So if this entire expression on the right hand side is replaced by a Shoaling coefficient Ks, then you notice that this equation right now becomes H over H0 equals to Ks, or basically H equals to Ks times H0, or basically H over H0 is equals to Ks, which is the right hand side. So these are just different way of rewriting the same equation. They all come from here. So what we have just did is that we introduce the Shoaling coefficient, and we say that H equals to Ks times H0. But you notice here there's another prime that is introduced into the equation. H equals to Ks H0 prime. Okay, we use H0 prime to refer to unreflected deep water wave height. So H is the wave height. H0 is the deep water. H0 prime, the prime is unreflected because we want to study only the effect of shoaling. We don't want any other effect. Specifically, we don't want to look at refraction effect. Okay, there will be no reflection in the deep water, so it's not important for us to mention, but there might be reflection, but we are going to assume that there is no reflection. So this is unreflected deep water wave height. So if we know what is the unreflected deep water wave height, we can calculate the wave height at any other location which has a different water depth if we know what is Ks. Now previously in the first topic we have looked at how we can calculate the wavelength at different water depth. So it is possible for us to calculate the wavelength for different water depth. It is possible for us to calculate N for different water depth. That means we can get Ks, the Shoaling coefficient. And once we get the Shoaling coefficient, and if we know what is the deep water unreflected wave height, we can find out what is the wave height at any location if we know the water depth. We will look at this in example later on. This figure shows the value of the Shoaling coefficient Ks. as we move from deep water to the shallow water. So on the horizontal axis below, we have the relative depth. We remember when relative depth DOL is more than 0.5, so everything on the right hand side here is the deep water, and DOL less than 0.05 is shallow water, so everything on the left from here is shallow water, and everything from here to here is the transitional water. The vertical axis here is the H over H naught prime. So basically the vertical axis here is the Shoaling coefficient, because Shoaling coefficient is defined as the ratio of the wave height at any location compared to the unreflected deep water wave height. So we notice that over here in deep water, the value of Shoaling coefficient is approximately equals to 1. This part equals to 1. As the wave moves in deep water, the wave height has no changes because it remains in the deep water. But when the wave moves to transitional water, you notice that the curve starts to drop, which means H over H naught prime now becomes less than 1. At some point, it will drop to a minimum, meaning that the wave height in this part is less than the deep water wave height. However, as it moves closer to the shoreline, when D over L decreases further, it started to rise. It means that H over H naught prime now becomes more than 1 over here. When it becomes more than 1 over here, means that the same wave that started right here now has much larger wave height. If it reaches closer to the shoreline, it can be 20% higher than its original wave height in deep water. If it goes further closer into shallow water region, it can be 1.4 or 40% higher, 50% higher, or even 60% higher than its original wave height here. So from this curve, we know that the Shoaling coefficient shows how the wave height changes with the relative depth. Wave height is almost a constant in deep water. It reduces slightly in the transitional water, but eventually start to increase, and by the time it reaches shallow water, it is much higher than its original wave height in deep water. Let's look at an example here. Consider the wave from example 4.6-1. That's the one that we looked at in the previous lecture on wave mechanics. Okay, consider the wave from the previous example when it has propagated into a water depth of 10 meters without refracting, and assuming the energy gain and energy losses can be ignored, which means that P is a constant. Determine the wave height and the water particle velocity and pressure at a point 1 meter below the still water level under the wave crest. Here the question asks us to assume fresh water. So that will be the density value that we are going to use later on. What we want to determine now is the wave height and the water particle velocity, and then the pressure. Alright, let's gather the information we have. Actually, it's from the previous example 4.6-1. So we are given that the wave actually begins in deep water where the water depth is 100 meters. It has a wave period of 10 seconds. It has a deep water unreflected wave height of 2 meters. And so we are able to solve previously that its wave celerity is 15.6 meters per second and the wavelength is 156 meters. So these are all from the previous information. Actually, all we need is this part of the information. C0 and L0 are calculated. So you have to look back at example 4.6-1 how we obtain C0 and L0 if you forgot. Alright, so now this wave has moved to a region whereby the water depth is only 10 meter. So we are going to apply the general expression for the wavelength from the linear wave theory. So we have L here and we have L here. We have G times T squared, T equals to 10 over 2 pi. We have tangent hyperbolic 2 pi D, D equals to 10 over L. Here we have L on both sides of the equation. It needs to be solved by trial and error. So we found out that the deep water wave, which has a wavelength of 156 meter, when it moves to a location which is only 10 meter deep, then the wavelength right now has reduced to 92.4 meter. Okay. So if we already know the wavelength, we can find out K. K is 2 pi over L, that's the wave number. So this is the wave number. And next, we want to find out the value N. N is the ratio of the wave group celerity compared to the individual wave celerity. So this is the expression. So basically, all we need is K and D. We already know K from here, and we already have D equals to 10 meter in this location. Alright, so we have 2 kd over sine hyperbolic of 2 kd. So we perform the calculation, we have 0.874. Remember that N is equals to 0.5 at the deep water, and eventually will approaches or equals to 1 in the shallow water. So up to this stage, we already found L. We already have L0 as well. We have found N, and we have N0 as well. So we can proceed from here to solve the wave height using the Shoaling coefficient. From the Shoaling coefficient, we know that H is equals to Ks times H0 prime, and Ks can be written in this form, so that H equals to 2. 2 is the deep water unreflected wave height, and the square root here is the Ks. So we have the L0, 156 meter in the deep water. We have 2 here, which is the 1 over 2 for N0 in the deep water. We have N, 0.874, the value at the water depth of 10 meter, and the wavelength at the water depth of 10 meter is 92.4 meter. So with all this, we are able to calculate that the wave height at 10 meter is 1.97 meter, which in fact is slightly lower than 2 meter. Now we can also use the plot for the Ks in the previous slide. Alright, we can use that to determine the deep water, how the deep water wave height has changed. So if we want to use that chart, we can first calculate D over L. D is 10 meter at the location that we are interested in. L is 92.4 meters, so DOL is equals to 0.11. We go back to the chart. For DOL equals to 0.11, we can read the Ks value from the vertical axis, and from there we should be able to work out the same wave height. Now you won't get exactly the same answer, but don't worry about that. Okay, it should be fine as long as it is close enough. So next we want to proceed to determine the water particle velocity at the crest, located at a position which is 1 meter below the still water level. So Z equals to -1. So we use the equation for the water particle velocity. We have this part, which is the magnitude. We have this square bracket, which is the hyperbolic term, and we have this cosine, which is the phase term. Okay, since we are looking at the crest, then the cosine term must be equals to 1. Alright, and whereas for the hyperbolic term, we know d is equals to 10, z is equals to -1. That's why we have k times 9 over here, and we have k times d equals to 10 over here, pi h from here, t is still 10 meter. So at this location, which is 10 meter deep, but 1 meter below the water surface, the water particle motion has a maximum velocity of 1.01 meter per second. And since we are talking about the crest, so the vertical component of the velocity will be equals to 0. Next, we try to solve for the wave pressure as required. Here we have the equation for the wave pressure, and we recall that it is made up of the hydrostatic component and also the dynamic component. The hydrostatic component, we have rho g, we are using the freshwater density, and z is -1. So you notice that the hydrostatic pressure is a positive value in the water column. Over here we have rho gh over 2. H is the wave height at this location where the water depth is 10 meter. We want to find out at this location what is the wave pressure, so we use the wave height at this location. And then we have the hyperbolic term. We have k, which is 2 pi over l. We have d, which is 10 meter. And so we have 10 here, we have 9 here because d plus z is -1. And lastly, we have the cosine term, which is the phase term, that equals to 1, because we want to find out what is the maximum pressure. If cosine is -1, then we will still get the same magnitude as the largest pressure. But of course, the cosine term fluctuates from 1 to -1, okay, in a typical sinusoidal function. So we are not interested when the cosine term is less than 1, because in that case the pressure will be smaller. We just want to know what is the largest pressure at this point. Okay, so we treat this cosine term as equals to 1. Unless we specifically want to know what is the pressure at a specific location and at a specific time, then we will solve the cosine term. And if we solve the cosine term, definitely the pressure that we obtain will be less than this answer. This answer is the maximum pressure that will be recorded at this water depth of 10 meter, 1 meter below the water surface, when the wave height is 1.97 meter. The pressure is about 19 kilonewton per meter square. Let's do this example as an exercise, and we will discuss it in our online session.